So we know that a current is our electrons moving through a wire. And for those charges to move, we need an electric field. And if we have an electric field, we have voltage. And now we need to try and pull all those things together. And that's what Ohm's law does. It provides a relationship between voltage, uh, current, and resistance. How do we determine how much charge is moving through a given circuit? Well, here we have to talk about not only voltage, which is V, and current, which is strangely I, but we have to talk about what that resistance is. Okay, so if I have a water tower, right, and I have a pipe that goes through here, and it's, say turning a generator, if I make that generator really hard to turn, it's going to slow down the flow of water through our pipe. Same thing here. If I have a strong resistance, then it's going to slow down our current. And this gives us Ohm's law. And this is a crucial law for circuits. And it makes sense, right? It's just the amount that's flowing is equal to the sort of potential difference of what's pushing the current divided by how hard it is to push it. Okay, so if I have a lot of force, potential energy or potential difference between 2 points and not much resistance, I'm going to get a large current. If I have a whole bunch of resistance, my current's going to be a lot lower. And so you can manipulate this all different ways, right? So V equals I times R, right? And we'll use it in different ways. But that's an important law there. The unit for resistance is an ohm, which is symbolized by this omega here. In a wire, I told you before that there is resistance in a wire, right? That results from electrons colliding with the molecules of the wire itself, which adds thermal energy to those atoms. So if I have an electron that's moving through a wire, and rather than running into another electron and adding energy to that other electron, it actually collides with a molecule of the wire. It's going to add kinetic energy to the molecule of the wire, right? And we know that what is temperature? It is a expression of the kinetic energy of those atoms. So if you're adding kinetic energy to the wire molecules, you're going to have a wire that heats up. Resistance more often results when the electrons are doing electrical work, heating up a heating wire or turning an engine or lighting up a lamp or something like that. Okay, so let's talk about this pipe metaphor a little bit more, just because I think it's a really useful one. So remember Poiseuille's law? Of course you don't. That was months ago, right? So what's Poiseuille's law? It's the law for viscous flow through a straight pipe, right? And we started when we talked about Poiseuille's law, we said, well, the flow of water through the pipe is equal to the difference in pressure over the resistance of the pipe. In other words, like voltage, pressure is how much force is pushing through there divided by the resistance of the pipe. And it came out the resistance of the pipe had to do with the length of the pipe, with how big the pipe was, and with the viscosity of the fluid. When we look at Ohm's law, it looks very similar, right? We have, again, our flow is equal to our force divided by our resistance. And here our resistance is size of the pipe, size of the wire, right? Length of the pipe, length of the wire, and then a material coefficient, right? Here we use viscosity. Rho here is our resistivity of the material. So if our material is made from copper or gold or iron or whatever, that's going to define that. So it's kind of parallel to our viscosity. These laws say the same thing. Flow through a pipe is determined by the potential difference divided by the resistance to the flow. Okay, and it's easy to think about if you're trying to imagine what's happening in a circuit. It's good to go back to this. And it's just sort of interesting to note how similar this is to that. All right, so we can talk about current. We can also talk about power. The amount of current and the voltage both affect the power that can be supplied to a device. So power, when we talk about watts, right? So I have a 25-watt light bulb. That's power. Is going to be a combination of how much charge and basically how hard that charge is being pushed, right? The power is the voltage of a circuit times its current. Again, thinking of water from our reservoir or from a water tower, the power produced by a generator in say a dam would be affected both by the amount of water moving, right, and by the height difference. That makes good physical sense to us, right? If I have a dam and I'm releasing a bunch of water, that's going to do more to turn a generator. If I release that water from a larger height, it's going to have more kinetic energy, right? And it's going to turn those generators more effectively too. And so the same with an electrical circuit, right? The power of our circuit has to do both with that potential difference, how much potential energy difference there is between 2 points, and how much charge we're pushing through that particular point. Now we can combine that power law here with Ohm's law, and we get power is equal to V squared over R, or power is equal to I squared over R. And those can be useful in different situations. But let's take an incandescent light bulb that's 25 watts, right? Something like this. Why is it 25 watts? Well, it's 25 watts has to do with the resistance. It's assuming you're going to use that at a household voltage, right? A household voltage is about 120 volts. And so you're going to, the way an incandescent light bulb works is you pump a bunch of current through a very thin wire and it glows. Okay, it heats up and it glows, which is why they're so energy inefficient, because you're spending all this energy heating up this wire. But the way you control how much current is going through there is by controlling the resistance. So we take this version of our power law and we say, well, we know the voltage in a household circuit, right? We know what the power is, and so we can actually determine what the resistance of that wire is. So what happens if we take that light bulb and we plug it into a 240 volt circuit, which is a big circuit in a household, like you'd use for an oven maybe, or a dryer. What's going to happen is it's going to have that same resistance, right? It's going to have a higher voltage, and its current is going to become much higher. And it's basically going to shine very brightly, briefly, and then burn out because it's going to destroy that wire. So that's how voltage, power, current, and resistance relate to each other. And we'll use these equations a lot to link all four of those different concepts together.